Alright, let's get started with our unit test for force and translational dynamics under the course physics. Let's go. Alright, for the first question, what do we have? A child pulls a 4.5 kg sled, okay, along a snow. So we have a mass acting below here, which is 6.5 g Newton along the snow. So force is in this direction. 7.5 Newton, angle 30 degree above the horizontal. So you have 30 degree here. Theta is equals to 30 degree. The sled is accelerating, so you have acceleration in this direction of 0.15 meter per second square. Determine the coefficient of friction mu between the snow and the sled. All right, so we have the normal reaction pointing here R, and obviously friction would act in this direction, which is F of friction. Now we know that the sled is accelerating towards the right, so the resultant force is in this direction, and hence this force must be greater. So when we write F equals to ma, resultant force will be basically this force, which is 7 point. So this is 7.5 with the force angled. So this is 7.5 cos 30, and we also have this added to the normal reaction force. So this is 7.5 sine 30. So F equals to ma. F equals to key 7.5 cos 30. Okay, this direction negative. Now this, because the object is moving, we would have maximum friction, which equals F max equals mu times R. So mu is what we want to find. So this is mu. And what about the R? We can find R by R equals to 6.5 times 9.8 negative 7.5 sine 30. If we do the calculation, we get the R. So mu times R, and we have to calculate this first. So 6.5 times 9.8 minus 6.5 times 9.8 minus 7.5 sine 30. 7.5, we have sine 30. Now the problem is you have to change this to degrees in order to get the correct value for sine, and we get 59.95. Okay, so this is 59.95. So mu times 59.95. Okay, 6.5 times 9.8 negative 7.5 sine 30, 59.95. This thing is equal to the mass, which is 6.5 kg, times the acceleration, which is 0.15. And from here we would be able to find the value of mu. So 7.5 cos 30, right? So 7.5, we have cos 30. Okay, 7.5 cos 30 negative mu. So let the mu be x, negative x, times we have 59.95, 59.95, and this thing equals 59.95 equals 6.5 times 0.15. 6.5 times 0.15. What do we have? We have and the two significant figures. Okay, so 0.092. Two significant figures means 0.092. This is the mu value that we are looking for. And let's see. There we go. A person stands in an elevator that is moving downwards. All right. Which of these forces act on the person? Upward force from the elevator cable, upward force from the elevator motor, upward force from the elevator floor. That's correct, because upward force from the elevator cable is not on the person, and definitely not the motor. Downward force from the earth, obviously, it's acting always at all objects, so this is correct. And upward force on the elevated floor, because the person is only standing. Other forces, like these forces, are contact forces. So if the person does not have any contact with these, how can they have an force, right? The person is only contact with the floor, and hence we can have, the upward force. But the earth force is not a contact force, it's a non-contact force, so it can act independently. So that's why we select C and D. Okay. All right. Block A of mass MA is on a frictionless horizontal surface. It's connected to a spring of constant K, and that is attached to a wall. Block A is also connected to a hanging block B of mass MB by a string that passes over a pulley. The system is at rest. All right, so left equals right. The resultant force is 0. The spring is stretched by an amount del x compared to its equilibrium length, which expression is equal to the mass of mg, assuming an idle spring, idle pulley, and idle string. Well, idle spring is just a spring that has negligible mass and exerts a force that is proportional to change in its length as measured from its relaxed length. An idle pulley has negligible mass and rotates about an axis to its center of mass with negligible friction. And lastly, the idle string, well, it is an negligible mass. It has a negligible mass and does not stretch when under tension. The tension is the same at all points within the string. Because the entire system is, at rest, we know that the tension must equal the weight of this block, which is mg, or to be specific, m of b times g. This would be equivalent to the leftward force that we are getting on from the spring. So um, that we are getting from the spring on this block. So we know that F equals to K times X being the extension, okay, or the del X. So this thing must equals K times del X. And they have asked us to find the mass of block mass of block B. So as you can see, it's just this thing divided by G, because when we divide by G, it can cancel out, and we've made M be the subject. So there we go. D is our answer. All right, next question. A block is on a horizontal surface with negligible friction. Okay, here's a horizontal surface with negligible friction. The block is attached to a force sensor by a string of negligible mass. The other end of the string is attached to a motor that spins with constant speed. A top-down view of this setup is modeled below. A group of students adjusts the motor so the block moves at various speed. All right, they keep the block's mass and the radius of the path are constant. They record the reading of the force for each. So as we can see, we're measuring F. So F is the dependent, which means it must be on the y-axis. Dependent variable. Pardon my handwriting and spelling, just rough thing. And we are varying. What are we varying? We are adjusting speed, or V. So V is the independent one, the one we choose to change, independent variable. And that's why when we plot a graph, it will be on the x-axis. So x-axis we have V, on y we have F. They record the reading on the force for each new speed, which graph could represent F as a function of V. So now we need to know the relation between F and V in order to understand what kind of graph we can expect. And in order to do so, we know that in a circular motion, the centripetal acceleration is provided by the v squared divided by r. And from Newton's second law, F equals to ma, the acceleration. If we plug this one here, we get F equals m times v squared by r. And when you plug in r, like when you take out r, so mv squared times 1 by r, and you're not uh you know sorry, you're not plotting v square here. You are plotting v square, and apart from r, you should also take m. So you have F equals to m by r, which stays constant. Mass and radius stays constant, so it's just a constant, times v square. If it was a v squared thing, then you could expect something like a straight line through the origin. But because you're plotting v instead of v squared, basically how a quadratic equation, a quadratic shape looks like is what the shape of our graph. So C matches our expectation, and so we select C. There we go. All right. So a box of mass m is on a frictionless incline that makes an angle theta with a horizontal force. Okay. A force F is applied to the box parallel to the incline as modeled below. So this is a frictionless. We don't have any friction, but we do have weight, which is acting below here, which is mg. Because this is because this is theta, this will also be theta, and we can prove that by saying that this thing is definitely 90 degree. Okay, and if this is 90, this will be 90 minus theta, and this entire thing is 90 minus theta. So 90 minus 90, 90 minus 90, positive theta, you get theta. So this is how we get theta from here. So if we resolve this into these two components, we get mg sine theta, and here we get mg cos theta. And we have the reaction, normal reaction force, R, equaling this thing. And if the ball accelerates up the incline with magnitude A, what is the magnitude of the applied force? So F equals to m, resultant force equals mass times acceleration. Resultant force is upward, so F must be greater. So F minus the portion of weight that is resisting the motion. We don't have any friction here, but we do have a weight component opposing the motion. So mg sine theta equals mass times acceleration. They want us to find F, so we make F the subject. So F equals to m a plus g sine theta. So this matches m times a plus g sine theta. So B is our answer. All right. Next question. Blocks A and B of masses MA and MB respectively are connected by a string that passes over a pulley. Block A is suspected from the string and block B is on a frictionless horizontal surface as modeled below. Which expression represents the magnitude of acceleration? Okay, because it's a frictionless horizontal surface, we don't have any force that is opposing the motion. So here we have tension T that is pointing outwards from B, point of observation. We always label tension pointing outwards from our point of observation, and from here it's pointing here outwards. And the force that is pulling A is the mass of A times G, the weight of this block. Now acceleration would definitely be in this direction, and if we apply the F equals to ma Newton's second law on block A, resultant force here in this case is ma times g. This is the bigger force because it is moving downwards, minus the t, which acts as the impedance or the resistive force, times m of a times the acceleration. Now because both of these blocks are connected by a same string, they essentially perform or essentially work within a same system, and hence they have the same acceleration. So we can write this as the same symbol. So let's say that is A, and we can make T subject from here because we want to find A. So if we make T subject, we get positive m times A equals to T. So this thing is positive, it becomes negative here, negative, because this thing is positive, and this negative becomes positive here. So this is what we get. So, and regarding the block B, the only force is T. So F equals to ma. If we apply this, T is the only resultant force equals mass of B times acceleration. Now, we have the same tension, so we can equate them. We can make them equal and write that, hey, mb times A equals mag negative ma times A. and they want us to find the magnitude of the acceleration. So we make A the subject. So what we can do is mb times A positive ma times A equals mag, and if we make A the subject, we have mv plus ma equals mag, and for A we have mag time over mb plus ma. So mag matches this, and so does the denominator. So B is our answer for this question. Moving on. So during lift off, an astronaut experiences a maximum acceleration of 30 meters per second squared. Suppose the astronaut modeled below has a mass of 65 kg. What is the approximate magnitude of the normal force exerted on the astronaut by the seat during the maximum acceleration? Assume the surface of the seat is parallel to the Earth's surface. So we have a force acting in this direction, which is the weight, which is 65 g Newton. And we have a normal reaction, which is R. The maximum relation is this, and what is the approximate magnitude? Well, F equals to ma, R minus 65 times 9.8 equals to mass, which is 65, times the acceleration, which is 30. So R would be 65 times 9.8, 65 times 9.8 plus 65 times 30, which is 2587. So if we round that up, it is 2600. There we go. Okay, next question. Which free body diagram correctly models the forces acting on the ball when it is at the location shown in the diagram? Assume air resistance is negligible. Okay, so a ball is kicked into the air with a force Fk after losing contact. It's no longer contact with the force, so F is not present anymore. It is one-time thing we apply, and that's it. It keeps on moving with inertia. Force is not present. So any option that shows me Fk, it's wrong. So A and D wrong because it lost contact. If it was still in contact, so we would have considered that, but it is not. The ball follows a parabolic path shown below from the left to right. The only force that is applying because air resistance is negligible, so the only force is the weight of the gravity, which always acts, downwards towards the Earth. Earth is not in this direction. Earth is in this direction. This one, C. There we go. Okay, next question. A car can drive around the curve at a speed of v with no radical friction present between its tires and the road. Okay. It can drive around a curve at a speed v with no radical friction present between tires and the roads. Suppose the radius of the curve decreases to 0.8 r. The angle of the ramp remains theta, and the car maintains the speed of v. Which free body diagram could represent the forces acting on the car? Consider only the forces or force components in the plane of the image. Assume the car does not slide. Okay. All right. So here is the full picture. A carved highway on ramp is banked at an angle, as you can see with respect to the horizontal. That makes a horizontal circular arc of radius r, as modeled below. So okay, so we have the weight, the mass, right? We have the mass. We have the mass acting, or the weight acting in this direction, which is mg, and we have the theta acting in this direction. So we have a component of mg sine theta in this direction, mg cos theta, which acts as the normal reaction force. Now, how can the car drive around the curve at a speed of v with no radical friction? Who is providing the centripetal force necessary for the circular motion? Well, it's the component of this. It is the component of this of its weight. Component of its weight is what acting as the that is being resolved, as you can see, mg sine theta. This thing is acting as the centripetal force, so that's why we don't need any friction between that. Now the radius of the car decreases, so radius of the curve decreases to, like, the car moves a bit, um, a bit closer. So let's say this is the shape, okay, something like this, okay. The angle of the ram remains theta and the car remains at a speed v. So what will happen? Cause the forces acting on the car. So let's see. Okay, we don't need this, except for we need that acceleration is equals to v squared by r. So when you reduce r, you're reducing the r, acceleration needs to be increased in order to maintain the same v. In order to do so, F equals to ma. If we have constant mass, if we increase the acceleration, the net force also increases. So f of g always points downwards. This is correct, consistent throughout. Fn always points upwards. I mean parallel, perpendicular to the plane, but we have a change in direction now. Here is the question. We know that friction will come now, so D cannot be our answer. And friction always acts parallel to the surface, which is not plane left arrow, uh, parallel to the ground. So B cannot be our answer. Now the question is, where will the friction occur? Whether it is at C or at A. So friction can occur. They didn't say that it's on a frictionless surface. And how would you balance? Like, you have reduced R, right? So in order to resultant force or the centripetal force in this direction, if you want to increase this, sine theta, this is how the graph is for sine theta. So theta remains the same, right? Theta remains the same. So we don't need this because theta remains the same. We need a component of something added to this in order to increase the resultant force, and this is the friction. So it must act in this direction. So C should be our answer. There we go. All right. Orbital data for 4 of Jupiter's moons are shown below. The orbital radii are measured from Jupiter's center of masses. So this is Jupiter, and you have moons here or something. And the orbital radii is measured from the center. Okay? And the orbital period t refers to the time taken for the moon to complete an orbit around Jupiter. A graph of t squared and r cubed for the 4 moon shown moons is shown below. Okay. If another moon was discovered around Jupiter with a period of 14.1 Earth days, its orbital radius would be most nearly. Okay, so 14.1 is the Earth days, but we have t squared here. So we will not be able to find 14.1 here because it's squared. So you have to square that and look for 190 or roughly 200. So 200. And when we do so, we get a value something like, this is 475. Yeah, we get a value of 475, and this is times 10 to the power 16. And we have to cube that because they have asked for orbital radius, so the radius cube. So cube root, and cube root is the same thing as to the power of 1 divided by 3. So we have 475 times 10 to the power 16. And this is the answer, but we have to round it up to three significant figures. If we do so, what do we see? It's 168, and then we have four zeros. But yeah, 168 and we have four zeros. So this is our answer, D. There we go. Okay, moving on. The graph below shows the magnitude of gravitational force two objects exerts. Okay, so one object, two object shows the magnitude of gravitational force Fg. Two objects exist on each other as a function of distance between their center. Okay, so the more away you are, as you can see, that as the discrete r increases, the Fg decreases. Okay, when they're separated by r naught, they exert a force on F naught, as you can see here. It's shown here. Complete the R or Fg pairs to show the correct force magnitude when the separation is double, triple, and quadrant. So, what happens when you double that? As you can see, it gets reduced by 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. Okay, so this is 1, 2, 3, 4. What happens when you double it? It's got reduced to the by amount of 2 square, which is 4. So 2r you have 1 by 4. For 3 it would be 1 third squared, 1 by 9. For 4 it would be 1/16th, because we know that you have F, or the centripetal force, the gravitational force is inversely proportional to the square of the distance between them, separation distance. This is the reason. Okay. Two objects A and B are hanging in top of a vacuum chamber on Earth. Okay, vacuum chamber, hanging, A, B. Two objects. Top of vacuum chamber on Earth. A is less massive than B, so B is more massive. This is B. Okay, this is B. A is less massive than B. The air is removed from the chamber, and A and B are dropped from the same height. Okay, same height. We are dropping this to the ground. Now, which statements are true? The inertial mass of A is less than the inertial mass. This is not true. The mass is different. Inertial mass is not the would be change. But here they have mentioned A is less massive. All right. The gravitational mass of A is less than the gravitational mass of B. The magnitude of A's acceleration is less than the magnitude of, no. Because it's a vacuum, the acceleration would be the same, which is the acceleration of the Earth, which is g equals to 9.81. And the magnitude of A's acceleration equal, yes, this will be true because we don't have A, and both of them would only experience the gravitational acceleration. Now, regarding the gravitational mass of A is less than the gravitational mass of B. So, whether this is true or not, MA, gravitational mass of A, is less than the gravitational mass of B. This is true. Same for inertia. But here in this case, we won't have any inertia. Like, this thing is not applicable in this case. This is true generally, but here specifically, it's not relevant because it's not making a difference. Only the gravitational force is what applying in this case. So I'll go for B and D. Okay, so A is also correct. Yeah, A is correct, but it was not relevant. This is what I thought. So, which statements are true? Yeah, this is generally true, but not relevant. That's why I didn't select. But it's correct though. NASA is currently working toward the goal of sending humans to Mars, where the surface gravitational field strength is 3.7 Newton per kg. Suppose an astronaut training for a mission to Mars waits, okay, on Earth. So mg equals 712. So this is the new m equals to 712 divided by 9.8. This is his mass or her mass. Suppose an astronaut training for a mission to Mars weights testing on Earth. How much would the astronaut weigh on the surface of the Mars? Which is 712 divided by 9.8. 712 divided by 9.8. This is the mass. 9.8, not 98. 712 divided by 9.8 is the mass. And this thing times 3.7 Newton per kg. Times 3.7 Newton per kg. So they have asked us to give the answer in two significant figures. So this is 270 Newton. 270 because 268, so 270 Newton. Last question. A Stuntwoman of mass m, so mass m, g, falls into the net during the filming of an action movie. At the instant shown below, the net exerts an upward force on the Stuntwoman of magnitude f, and she has an upward acceleration of magnitude a. Which of the following is the correct expression for, okay, F equals to m, right? So F minus mg, because we have an upward acceleration, F must be greater, equals ma. And so for a, we do this and we have to divide, so m by f minus g. So as you can see, B is our answer. And that's it. This is the end for our unit test.